All right, here we go. Welcome to today's physics lesson. Today, we're going to be working some more with one-dimensional motion. We're going to focus on how you deal with the displacement of an object that's accelerating. And so by the end of this video, you're going to get a whole boatload of new equations, which ultimately is what this video boils down to, is some new equations and how to use them. But you should be able to use those equations too. If you're given, any three of these, you ought to be able to find the two missing ones, basically. Is, I believe, the way this will boil down. Boil down? Is that a thing? Here we go. All right. So far, we've already learned how to calculate the displacement of an object that's traveling at a constant velocity. But what happens if the velocity is changing? So to answer it, let's look at two simple examples. All right. So in this first example, it says suppose a car travels at 30 meters a second. So as usual, let's write down what we know. So 30 meters a second is a velocity of some sort. We'll decide what kind it is in a minute. For a time of 6 seconds, how far will the car travel? So we're looking for a displacement, all right? But we need to be more specific about this velocity. And the idea is, it says the car travels at 30 meters a second for 6 seconds. So this is a constant velocity, right? And so we can just simply call this average velocity, right? Or even simpler, just that is the velocity, right? It's going to go 30 meters every second for 6 seconds. So you guys all know how to do this. Displacement is average velocity times time, right? So we're going to go at 30 meters a second. So every second we're going to go 30 meters. So in 6 seconds we'll go 180 meters. Cool. So hopefully that was pretty easy. But the reason that it was easy is because of this, because our velocity was constant. Because what it meant was that literally every second the car was traveling, it traveled 30 meters. All right. But in the real world, that's not usually true. Cars don't always travel at the same speed. They speed up, they slow down. So let's take a look at example 2. So now we've got a car that speeds up from rest to 30 meters a second in 6 seconds. How far will the car travel in this time? So upon first glance, this looks like the same problem, right? Because if you read it quickly and just look at the numbers, you're going to go, well, let's see. The velocity is 30 meters a second, and my time is 6 seconds. So velocity times time gives you 180 meters. But that would be inaccurate because in this example, the car is not always going 30 meters a second. It begins at rest. So what that's telling us is that our initial velocity is 0, and it's our final velocity that's 30 meters a second. So if you picture the car speeding up, it's not until the very end of these 6 seconds that the car actually gets to 30 meters a second, right? So it's actually going to go less than 30 meters each second, because it doesn't travel that speed until the very end of the time. All right? So this is our given information, and we're trying to find, just like in the last problem, the displacement. Okay? But the problem is the velocity is not constant. All right? So one option is we could try to use displacement as average velocity times time. Remember, I put the line over there by accident. The problem is we don't know the average velocity. All right? So I'm going to show you 3 different ways that we could solve this problem. Okay? And ultimately, you need to know all of them because different methods will help you in different circumstances based on what your given information is. All right, so here we go. Option 1, we can find our average velocity. I'm realizing I forgot to correct this. All these V's of the lines over it are V average. I think I talked about that when we learned about average velocity. All right, so here's a new equation. One option is we can use the equation average velocity is Vf plus Vi over 2 to find the average velocity. I should comment, this only works if the acceleration is constant. This is actually a super, super important point. You can only use that equation, Vf plus Vi over 2, for a problem in which your object is accelerating at a constant rate, okay? Which, for us, as long as we're talking about sort of one chunk of the object's motion, that will always be true, all right? That's what's happening here. We got a car speeding up. We're going to assume the acceleration is constant. So here's what we can do. We can find our average velocity. So remember, we knew our Vi was 0. We knew our Vf was 30 meters a second. We knew our time was 6 seconds. So I'm going to use this to find my average velocity. And it's actually exactly what you'd think it is, right? You're just averaging the starting and ending velocities. So let's see. So our Vf is 30. Our Vi is 0. Divide it out, and you get the average is 15 meters a second. Now, What that means is exactly what it sounds like. The car averaged 15 meters each second. There were some seconds where it went more than 15 meters, and other seconds where it went less than 15 meters. But on average, the car traveled 15 meters per second each second during these 6 seconds. Okay? So that is the average velocity for this time interval. All right? So now what we can do is we can find our displacement. Displacement is average velocity times time. We know we're going at 15 meters a second on average for 6 seconds. Multiplied out, you're going to get 90 meters. Okay, so there's our displacement. Okay, notice we went less than 180 meters because remember, it wasn't until the very end of the time that we got to 30 meters a second. All right. So what I'm going to do here, I'm going to combine these two equations. So this gives us a new equation. So what we just learned was this. V average is, that says average, Vf plus Vi over 2. We could, if we wanted to, write that as a half of Vf plus Vi. And we know displacement is the average times time. So by substituting, we get 1/2 Vf plus Vi times t. All right, my first year here at South, this became known as the Hernandez equation because Mr. Hernandez, I don't know, never mind, you don't care. All right, so there we go. Cool. That is one option. All right, option number 2. All right, so here's another new equation. If anybody's interested in where this equation came from, I'm happy to show you before or after class. I tend to find that students don't usually really care. Basically, what it is it starts with this equation, and then if you substitute this in for Vf, it gives you this equation. All right, so for all intents and purposes, this is really the exact same equation. So normally I would use this if you already knew the acceleration. So this option doesn't really make a ton of sense for this problem, but I do want to show you that it works. All right, so once again, let's start by writing down what we know. So our given information from the very beginning of the problem was we knew our Vi was 0, we knew our Vf was 30 meters a second, we knew the time was 6 seconds, and we're looking for our displacement, right? So if I decide I want to use this equation, in order to use it, I need to know my acceleration. So let's find our acceleration. So let's see, our Vf is 30 meters a second, Vi was 0, time is 6 seconds, divide it all out, and you get 5 meters per second squared. So now we can do this, right? Oops. So we're going to use this new equation again. Oh, never mind. All right, so here we go. So let's see, our acceleration is 5 meters per second squared. Our time is 6 seconds. Don't forget to square it. So that represents how far the object would go just due to the acceleration, but then we have to add on how far it goes because of the starting velocity, which in this case is 0. So our Vi is 0 times 6. So half of 5 is 2.5. Just the 6 is getting squared here because the time gets squared. Order of operations, right? You got to do exponents first. So I guess 6 squared is 36 times 2.5 does in fact give you 90 meters. Okay. So that is another option. It gives you the same result. Okay. Again, ultimately, this equation is useful if you already know your acceleration, which in this one we didn't. So this probably was not the best option of ways to solve this problem, but I want to show you that it works. All right. Finally, third option is this guy, which again I'm happy to show you where this comes from if you want. I tend to find most students don't really care. So this one's written a little bit differently. So the idea is it's got 4 variables in it, right? It's got acceleration, displacement, Vf, and Vi. Notice it doesn't have time. All right, so if you're ever solving a problem and you're like, I'm stuck because I don't know the time, then this is like your superpower. This is your safety net, all right? So it's written this way, though, because Um, so there's four variables. If you're given any of the three, you can find the missing one. Sometimes you'll use it to find acceleration. Sometimes you'll use it to find VF, whatever. But I tend to find that writing it this way is it makes the algebra on the equation the easiest, I guess, is probably the easiest way to say that. So in this problem, let's see, what do we know? We know that our VI is 0. We know our VF is 30 meters a second. We do know the time is 6 seconds, so really this wouldn't be my go-to equation to use this. And we're looking for displacement. So once again, if we wanted to use this equation, we'd have to find our acceleration. So, we already did this, right? We got 5 meters per second squared, just like we did in option 2. So now we can use this to find our displacement. So 2a delta x equals vf squared minus vi squared. So if I solve that for delta x, it gives me vf squared minus vi squared all over 2a. So vf is 30. Don't forget to square it. Vi was 0. Don't forget to square it. Divided by 2 times 5 meters a second squared. So 30 squared is 90, minus 0 is still, 30 squared is 900, minus 0 is still 900, divided by 10 gives you 90 meters. All right, so I get it, this was tedious. But I want to show you that all of these equations sort of work together. They give you the same answer. Sometimes students get stressed out because they'll say, well, what if I use the other equation? It shouldn't matter, okay? Which is kind of a good check, is that you can use different equations and get the same answer. All right, so there we go. All right, so let's try solving this one and kind of see if we can figure out which equation works best. All right, so motorcycle driving at 24 meters a second slows down at 3 meters a second squared for 5 seconds. How far will it travel in this time? So let's write down what we know. So we know that the starting velocity when we first see the motorcycle it's going at 24 meters a second. We know the acceleration is 3 meters a second squared, and the time is 5 seconds. The question wants to know how far the motorcycle goes. All right? Now, be careful. There's a mistake here. Because the motorcycle is slowing down, that means our velocity's got to decrease, which means that acceleration's got to be negative. All right? So we're looking for displacement. We know our initial velocity, our acceleration, and our time. So we pull out our equation sheet and we look to see which one of our equations is going to help us. And it turns out that this guy, I think, is going to be the one that works out for us. 1/2 at squared plus bit, right? Because we're looking for displacement and we know the other variables. So at this point, it's just a matter of plugging in your numbers. But just make sure you watch those signs. Let's see, our VI here is 24 times 5 seconds. All right, so look what we get. Let's see, so 5 squared is 25 times 1.5, so you're going to get negative 37.5 meters, plus 24 times 5 is, what, 120 meters? So the idea is, this part of the equation represents how far the motorcycle would have gone if it hadn't slowed down, right? If it just kept going at 24 meters a second. And then this adjusts for the fact that it's slowing down, okay? And so the answer we end up getting is, what's that going to give us, 82.5 meters? Okay. All right, so next example. A car driving at 28 meters a second slows down at 4 meters a second. If there's a brick wall in 100 meters, will he stop in time? So be careful here. So let's write down what we know. A car driving at 28 meters a second, that's the starting velocity. He's going to, again, slow down, so our acceleration is negative 4 meters a second squared. And people always make this mistake of going, oh, my displacement's 100 meters. But no, it's not. The 100 meters represents how far the car has to drive before it stops. We want the displacement to be less than 100 meters. So we want our displacement to be less than 100 meters. Okay, well, what displacement? Well, what do we want the car to do? We want it to stop. Aha! That means the final velocity is going to be 0, right? So what we want to do is we want to figure out what is the displacement that the car travels during the time it takes for the car to stop, and then we'll hope that that displacement is less than 100 meters, okay? So that's that. Now, we're trying to find displacement. We don't know the time. So that means we got to use our, we don't, with the time equation, all right, this guy, and plug in our numbers. So let's see, oh, well, I guess we can do this. Vf squared minus Vi squared all over 2a. So let's see, Vf is 0 squared minus 28 meters a second. Don't forget to square it. All divided by 2 times -4. Notice the negatives will cancel. And if you do this, it gives you 98 meters. So our car is safe. Hooray! Okay, so that's the deal with these. All right, so let's take a look at sort of how all of this affects us. The big thing I want you guys to understand is that the distance that the vehicle or the object travels each second is going to change. Okay? So I'm going to pause it here and I'm going to fill in these values here. These are the charts that we looked at, I don't know, a video or two ago, where we've got Roy dropping a ball and throwing a ball. And so in each problem, we know our initial velocity, right? Here the VI is 0, here the VI is 29.4, here the VI is negative 29.4. We know our time is 0, 1, 2, 3, 4, 5, or 6, or whatever. So we're going to find our displacement, right? All right. So let me run through and fill in the numbers real quick. Okay, so in this first table, here are the values you get. Take a second and make sure you understand them. The VI was 0 for each of these. Acceleration is negative 9.8, and then the time is whatever time it is, okay? But notice they get farther apart, right? In the first second, it went 4.9 meters. In the next second, it goes, if you figured out the difference between those is 14.7 and then 24.5. So it goes farther with each second because the distance that the ball travels each second gets farther because it's speeding up, okay? If you fill in the next chart, you get these numbers. In 0 seconds, it won't go anywhere. In the first second, it goes up 24.5 meters. After 2 seconds, it's at a height of 39.2. After 3 seconds, notice this is at the top of the path. So if you fill this in, you get 44.1 meters. And then it starts to come back down, and so your numbers decrease again. Remember, we're not measuring distance, we're measuring displacement. So the displacement is, after 6 seconds, is 0 because it's gone up and come back down to its original height. Okay? Now, again, to be clear, the acceleration here is negative 9.8. The time is whatever the time is in the chart, and your VI is 29.4. Okay? So it is totally worth taking a minute and plugging those values in and seeing what you get. All right? And then finally, in this last chart, our VI is going to be negative 29.4, and then the time is whatever. So real quick, here's the answers you get. I don't know if this tells us much, but all right, so there's the results you get. Let me point out here that here your displacements are negative, right? Because it's moving down below its initial position. Same in the first one where it drops the ball. All right. So let's see what else. Yeah, I guess that's that. All right. We are nearing completion here. All right. So sometimes you got to find the time. Okay. So this one says, suppose Roy was going to roll a ball down a ramp. If the ball began at rest and accelerates at 6 meters per second squared down the ramp, then find the time it would take the ball to roll each of the following distances. We're just going to do one of them, and then I'll give you the other answers. So let's do, I don't know, let's do 120 meters, okay? So here's what we know. We know that our initial velocity is 0 because he's rolling it from rest. We know it's going to go down the ramp, so the acceleration is 6 meters a second squared. We know that our displacement is 120 meters. It's a long ramp. And we want to know how long it's going to take. Okay? Now, real quick, some of you might be thinking, these numbers should be negative, right? It's moving down the ramp, so the displacement is negative. And that means that the velocity is going to get more negative, so my acceleration should be negative. And that's fine if you do it that way. With ramps, it's kind of a weird thing, right? Because remember, these positives and negatives are arbitrary. So some of you might be thinking, oh, it's rolling down the hill, that's negative. Whereas I look at it and just think of it as rolling forward, so it's positive. All right? Whatever. It doesn't really matter as long as you're consistent. The bottom line is if you make your displacement negative, you also have to make your acceleration negative in this problem. Okay? So, all right, so these are all of the variables that are in this equation, right? And so we're trying to find time. So it turns out that because our VI is 0, this part of the equation goes away, right? And so then when you algebraify this remaining bit and solve for time, you get this, okay? But again, that only works if your VI is 0, okay? So plug in your numbers here, and so let's see, we're going to get t equals 2 times displacement over acceleration square root e. So you get 2 times negative 120 meters over negative 6 meters a second squared. Notice these are either both negative or both positive, right? And then take the square root. So 240 over 6 is 40. Square root of 40 gives us a number 6.32 seconds. Okay, so there's the answer there. The reason I had you doing different ones was this. So if you find the time to go half of that distance, it doesn't turn out to be half of the time. It turns out to be 4.47 seconds. And the reason for that is it takes more time to go the first half of the ramp because it's going slower, right? Remember, it's speeding up as it goes down the ramp. So it's going to take more time to go the first bit than it will the last bit, okay? And so weirdly, it turns out that the time to go a quarter of the distance is half of the time. So this time ends up being 3.16 seconds, if you figure them out, okay? All right, so finally, what if VI isn't 0, all right? And I think I didn't even write an example for this. So let me do this real quick. So suppose we had a problem where, I don't know, maybe our VI is, I don't know, 24 meters a second, and maybe our acceleration is negative 3 meters a second squared, and maybe our displacement is, oh, I don't know, how about, let's go 50 meters, okay? And we wanted to find the time for that to all happen, okay? So there are two options. Option one is to use this equation. This would not be the way I would do it, all right? Because what ends up happening is you get this. If you plug in your numbers, I'm not even going to use units. You get 50 equals 1/2 times negative 3 t squared plus 24 times t, right? So rearrange this and you get 0 equals negative 1.5 t squared plus 24t minus 50. And so to solve that, you got to use the quadratic formula, which is rad. Quadratic. That is not at all how you spell that. Quadratic. Why can't I spell quadratic? Is it a T or a D? I guess that was right. Quadratic equation. So if you are comfortable with the quadratic equation and want to use it, you can totally do that. However, I tend to find that students always make mistakes here. There's that plus or minus with the square root, and it messes people up. So my recommendation is if you're solving a problem like this where you're looking for time and your VI is not 0, what I would do is this. Use this guy to find your VF, and then once you've got your VF, then you can find your time using this guy, all right? Even though it's 2 steps, I do believe that it is easier than solving with the quadratic formula, all right? So let's plug in our numbers and see what we get. So using this equation, we're going to get 2 times negative 3 times 50 equals VF squared minus 24 squared. All right, and do the algebra. All right, and you end up getting 16.6 meters a second. And now we can find the time. All right, so T equals VF minus VI all over A. So our final velocity ended up being 16.6 meters a second. The VI was 24 meters a second, and our acceleration is negative 3 meters a second squared. So you get like 2.46, 2.5 seconds. I guess we gotta go 2.5 seconds if we want to keep some semblance of accuracy with our sig digs. All right, so that is that. Okie dokie. We're going to spend a few days on this. There's a lot of information in this video. So if I freaked you out, it'll be okay. All right?